Hello, so my name is Takashi Sakajo from Kyoto University. Actually, the title of my talk is here. But as far as I see the problem and the talks I heard in this session, so I would like to add some new one, which is topological flow data analysis at the end of my talk. Okay, so let me start with and the talk is consists of two parts. The one is I'm going to explain what I have done in the year of 1998 to 2012 about the mathematics of vortex dynamics on sphere, which contains a very fundamental dynamics regarding on the vortex on the sphere. The second one is a recent application and some sort of the data analysis stuff applying to the geophysical flows. Okay, so let me start with the first part. So I'm going to explain about the flows on the sphere. So the purpose of this flow is mathematically we are going to understand the effect of closed surfaces to see the difference between planar and spherical flows. This is a very fundamental motivation what I have been studying for this flight flow. And the second motivation that we are going to consider the effect of rotation, so which is some sort of the geophysical relevance. So in order to understand this problem, we are going to use a toy model as a toy model of implicit and incompressible flows on a sphere. This is not a real flow because this is implicit and a two-dimensional flow. So, but this is a toy model, which is a conceptual model for geophysical flows. Okay, here is the mathematical description, what I have been talking about. So this is incompressible Euler equations in the spherical coordinate system. Theta and phi is taken like this, and the velocity field in the three-dimensional space is the radial direction 0 and the azimuthal direction u and v. So vorticity is defined by this formula. So, and the stream, when we introduce a stream function psi, like this formula, then we have the Poisson equation, where the omega is the given vorticity, and the psi is a Laplace and the stream function, and number squared, the S squared is a Laplace-Beltrami operator on the unit sphere. So then this is reduced to this very simple equation with respect to the omega. Okay, vortex dynamics is based on the fact that the vorticity is conserved along the path of a fluid particle, which is in the time derivative along the path of a fluid particle on the spherical surface is always 0. That means the Kelvin circulation theorem tells us that one can track orbits of these passive vortex particles having a non-zero vorticity at the initial moment, which gives rise to the vortex dynamics on the sphere. So the point is, in order to describe the evolution of this type, we are going to assume some special distribution of vorticity. So in this talk, I'm going to talk about these first two vortex distribution. So there are many famous vortex dynamics, which is known as point vortex, whose vorticity distribution is given by Dirac measures, which is point distributions. And the vortex seat, this is a line distribution, and also in other words, it is a discontinuity of the velocity field. There, the very famous one is a vortex patch, which has a constant vorticity in a finite domain, and a Stewart vortex, which is in the vorticity is represented by the exponential of the stream function. So in this talk, I'm going to focus on these topics. Right? Okay. So this is an assumption here. So suppose that there are n-point both seats located at theta m and phi m, and the circulation along the point is given by gamma m. So then the vorticity is approximated by this linear combination of delta functions, whose support is located at the location of the point both seats theta m psi m with the strength gamma m. So when we plug this in the vorticity distribution into the original Poisson equation, then we have the equation of motion for the location of this measure and of the support of the measure, which gives rise to the point vortex dynamics. So with this assumption, the Euler equations are reduced to a simple system of ODEs, which is an evolution equation for the theta m psi m. Looks very complicated, nonlinear ODEs. And also we have another way to describe the evolution equation for this point by embedding the point vortex on the in the three-dimensional Euclidean space. So we can use, in order to understand the evolution of interaction of these point vortices, we may use either of this spherical coordinates representation or Euclidean coordinates representation. These are the equations we are going to see how vortex structure interact with each other on the sphere. Okay, so since the equation looks very simple, the final dimension ODEs, we can, this equation allows the formulation with using the Hamiltonian dynamical systems. So this is when we introduce Hamiltonian H by this formula and the Poisson bracket by this, then the evolution equation here can be rewritten like this. This is a Hamiltonian formalism. By using this Hamiltonian formalism, we can understand how low number of vortex structures can interact with each other in terms of intervalbility. So when we introduce the three quantities, Q, P, and S, which is a summation of the X component and the Y component and Z component on the sphere, then these quantities are invariant. In addition to that, these quantities are in evolution with the Hamiltonian by using a Poisson bracket. And also, the P square plus Q square and S and H both are in evolution with each other. That means the general theory of Hamiltonian diagonal system can give this very simple theorem, which says the three-point vortices or three-point vortex problem is integrable. That means the solution can be described in terms of periodic orbits, which looks very easy to understand. So these are the papers given by this to dealing with this problem. So in addition to that, when we see the Q and P and S are also in evolution with each other, then if S, Q, P, which are invariant quantities, are always zero, then the four-vortex problem is still integrable. So this kind of problem can be considered in this paper, 2007. Okay, so that means we say the two-point vortex interaction, the three-point vortex interaction, the four-point vortex interaction is something very simply described by the integrable dynamical system. Okay, so here's another. That's right.
So the previous slide.
Yes.
S, not R in the last slide. P was Q.
Oh, sorry. This is P and Q and S. Sorry. This is typo. Okay, so the another problem is an existence of solution. Even if the problem is integrable, we still have a possibility to have some blow-up solutions. So there are two kinds of vortex collapsing solution in finite time. The first one is a very famous one, which is known as self-similar collapse, in where the 3 and the 4-point vortices collapse to one point self-similarly in finite time. And the assumption that the strength of the vortex point is satisfy this summation condition. So this kind of self-similar collapse can be found in the case of in the planar plane and in the case of spherical surface, but the second one is originally coming from the closed sphere, which is known as non-self-similar partial collapse, in which, as you can see here, 3 of 4-point vortices on the sphere can collapse at one point, 3 of the 4-point vortices collapse to one point, the other 1 point goes to the antipodal. The existence of this kind of collapsing solution is because the sphere is a closed surface. This kind of equation cannot be found in the planar vortex dynamics. Okay, so these are a very singular evolution for the very case of the very small number of point vortices. Okay, so this is enough. So next step, we are going to understand, and from dynamical point of view, so how these point vortex structures can be in an equilibrium state, which we call the vortex crystals. In order to obtain the point vortex, kind of the fixed state where the relative distance of the point vortices never moves for all time, we are going to understand how the distance between 2 point vortices evolves. So we are going to derive the equation of the relative distance, L alpha beta, which is the distance from the points x alpha and x beta on the sphere. So we derive the equation of the distances from the original ODEs, then we have this very complicated equations, which is in short, this term can be described by V alpha beta gamma, D alpha beta gamma. So in order to obtain the vortex crystal states where the relative distance has never been changed for all time, we need to solve the equation of this one, okay, for all alpha and beta and n. So when we see this equation for given strength of the point vortices, this is regarded as a nonlinear equations with respect to the location of the point vortices. This is very difficult to solve even numerically for a large number of n. But on the other hand, when we see this equation as a linear equation with respect to the strength of gamma, this is a null equation. So this A, which is the whose component given here, is regarded as a matrix which each component is determined by the configuration of the point vortices. Okay, so this is a change of way how we see the equations. So in order to obtain the vortex crystals in the sphere, we are going to solve these null equations for a given point vortex locations. So if the matrix A has satisfied this determinant A transpose A equals 0, then A has a non-trivial null space where the gamma belongs. So that means we are going to find the good locations of the point vortices whose corresponding matrix A has non-zero singular values. So in order to find this configuration, we use a singular value decomposition, which is defined by this way. By solving this coupled nonlinear and linear equation with respect to A and sigma I, then we have a singular values who are arranged and who is in order like this way, theta 1 through theta n, which is all positive or 0. And if theta sigma I, the singular value is at i's singular value is 0 for I is greater than k, then the gamma belongs to the null space spanned by the singular vectors spanned by and corresponding to the 0 singular vector. Okay, so that is a mathematical background how we obtain the configuration of the vortex crystal. So based on this observation, we are going to use a stochastic algorithm to obtain the vortex crystal, which is called the Brownian ratchet scheme. So the algorithm is very simple. So first, we distribute any point vortices randomly on the sphere. Okay? Then we compute the configuration matrix A and finding the small singular value, sigma mean. This is generally not 0 because this is generally the random point configuration does not form the vortex crystal. And then we allow each particle to execute in one random step on the sphere in order to produce a new configuration whose configuration matrix is given by A tilde. And then we compute the smallest singular value sigma tilde minimum. So when we compare these two the smallest singular values, then if the new one is less than the old one, we replace the configuration. Otherwise, we discard the trial. The process is repeated until the smallest singular values drops below a certain predetermined threshold, for instance, order to the 10 to the minus 10th, then this convergent configuration becomes a relative equilibrium because the configuration matrix of this configuration has the smallest singular values, lower than 10 to the minus 10th, up to numerical tolerance. Okay, so by obtaining this configuration, then compute a basis set for the null space in order to find the corresponding vortex strength. So this is a plot how the point moves randomly on the sphere, then converges to the configuration and vortex crystal state. So by using this stochastic algorithm, we can obtain wide variety of vortex crystal, which is a steady state configuration. Okay, here is an example for the 10-point vortices. So this is, I showed the 6 vortex crystals as examples. So this is a northern hemisphere, this is a southern hemisphere. As you can see, one point is northern hemisphere, and the other 9 is southern hemisphere. So we have another different vortex crystals by using the Brownian ratchet scheme. So as we may realize that these both crystals are antisymmetric, which is a non-trivial one. Okay, so by using this stochastic modeling, we are going to consider some very fundamental problem about optimal packing problem. So optimal packing of the circles of a sphere is given by this. So arranging endpoint on the unit sphere so as to maximize the minimum distance between the two of the point. So this is a very famous problem known as Tamest's problem. So for instance, for 12 circular spherical caps, this is optimal packing state. And when we increase the number of the spherical caps, these are the optimal packing state on the sphere. So the question is here. So do these optimal packing state give rise to the Vortex crystals or not? We are going to confirm this by using the linear algebraic approach, since we can obtain the location of the optimal packing by numerical means. Okay, here is a numerical method how we obtain the optimal packing state. This is also a stochastic algorithm known as the Ian method. So this is very simple. In the first step, we distribute n disjoint circles with a small radius delta, which is like this. Then we move these small spherical caps randomly. Then we expand their radius so that some of them touch until, we can expand the angles, the sum of the spherical cap and attach like this. Okay, so then we also move randomly, then expand the radius, and repeating this stochastic process, we finally obtain the optimal packing state by using this algorithm. Okay, so by using this idea, we are going to check the optimal packing state and the Vortex crystals. So this figure, this table shows the normal configuration where the optimal packing is attained. When n equals 3, which is equilateral triangle, this has the dimension 3 of null space. So this is an equilateral triangle. It gives rise to the Vortex crystals. So n equals 4, which is tetrahedron configuration, which is also given a Vortex crystal and optimal packing state. And then 5, there are two optimal packing state, packing state, which is tetrahedron and octahedron minus vertex. Those are also Vortex crystals. So from the 6, 7, 8, 9, up to 9, all optimal packing state gives rise to the Vortex crystal, but in the 10, this is not, because the null space of the configuration matrix has no singular space. On the other hand, on the 11 and 12, we still have both crystals when the point is on the icosahedron. Then this is the case, an icosahedron case. This is also gives rise to both crystals. So by using this table, we can say that regular polyhedra from n equals 3 to 12 attaining optimal packing form a Vortex crystals. And also we can show that their strengths can be identical, namely all the point both have the same strengths. Okay, so this is a result we have obtained the Vortex crystals. Okay, let us go change the topic to the Vortex, from the Vortex point dynamics to the Vortex seed dynamics. So the Vortex seed, as I have mentioned earlier, is a discontinuous surface of the velocity field. This is a schematic figure how the Vortex seed looks like. This red curve is the Vortex seed, along which the velocity field changes discontinuously, like this way. So then the location of the Vortex seed in this red curve is represented by a one-dimensional curve whose parameter is given by alpha, which is a Lagrangian parameter on the sphere, and t is time. So in order to understand the stability of this Vortex seed and the existence of the pole vortices, which is a model of the northern and southern vortex structure, then we introduce an additional point vortex at the north pole whose strength is gamma 1 and the south pole whose strength is gamma 2. So then we can derive the equation motion of this one-dimensional curve, which is known as Birkhoff-Roth equations. Okay, this is the equation, and this is a term coming from the polar vortices. We are going to deal with this equation and what happens if the solution evolves in long time. Okay, so the basic mathematical analysis is linear stability analysis. So a latitudinal vortex seat is a steady state solution, which is the same latitude, theta 0, and alpha is going along this latitude. So when we add a spectral disturbances to this steady state, then the standard linear stability analysis gives rise to the condition on the linear stability for this spectrum, which is given by this. For given strengths of the north and the south pole vortices and the location of the point and the vortex seat, if the wave number n is less than this value, the perturbation of the mode n disturbance is neutrally stable. Otherwise, if this condition is not satisfied, the high wave number is the wave number becomes linearly unstable. This indicates that if gamma 1 and gamma 2 and theta are fixed, for some low mode spectra become neutrally stable, but very large number of spectra are inevitably unstable because this is fixed and n can be large as we like. So that means, and also we can say that we can also have the exponential growth rate is proportional to the wave number, which is known as the Kelvin-Helmholtz instability. So in this sense, the vortex seat becomes linearly unstable. Okay, so we are going to see, so the vortex seat problem is, in the planar case, is also a very famous example having a singularity formation. So we are going to check if the solution forms of that equation, the Burke-Roth equation gives a finite time singularity. This is an evolution of the Fourier modes of the spectra from time 2.2 to 6.16. As you can see, as time goes from T4, 6, and 60.14 and 16 something, as time approaches this time, this spectra tends to the n to the minus 5/2. This means the solution of this vortex seat have the second derivative becomes infinite, which is known as curvature singularity. So this is a similar result on the planar case, and the spherical case that has a similar vortex seat singularity evolution. Okay, in order to see, okay, so by removing this singularity formation, we are going to add some constant in the equation to regularize the Burke-Roth equation. Then we can solve this equation by using a very simple initial configuration. This is a steady state, and the first mode perturbation is added in the initial state. So then we are going to see how the line vortex seat evolves for a long time. Okay, here is in a picture. When we choose the north pole is 1.5 and 3.5 pi, at the first moment, it looks very stable, but after a long time evolution, it becomes unstable due to the nonlinearity and the Kelvin-Helmholtz instability. Then at some time after 18, we can see a rolling up of vortex seat. Okay, so after a long time evolution, we see big spirals appear along the line of latitude. This kind of, so when we change the north pole and south pole, we see many coherent rolling up structures. This is a 4-point vortex spirals, this is 7, this is 1 big spirals, and this is 4. So this is after a long time evolution, depending on the strength of the point and the northern pole and the south pole vortices, the stability of the vortex seat changes, but after a long time evolution, we have many rolling up vortex spiral structure. This is a description of how vortex seat evolves. Yeah, okay, so here is a very quick notice about how this vortex structure evolves. So in order to understand the qualitative evolution of these spiral structures, we assume that these spirals can be modeled as a one big point vortices, okay? So that gives rise to a ring point vortex model to which we can use the point vortex dynamics to understand the long time evolution. So the ring configuration of the point vortices along the line of latitude is still a vortex crystal state rotating at a constant speed around the center. And so linear stability analysis has been investigated by many papers, and I have found in this paper that for certain choice of pole vortices, we find this kind of chaotic behavior. Okay, so let me show you how the, okay, so here, these points are vortex points, and blue one and the red one, are rotated in this way. At some time, this is a ring configuration, okay? And then it's going, because it is unstable, it is going this way, but the rotation direction changes abruptly in the opposite direction. The change of rotation direction cannot be predicted. This is because this is a chaotic evolution. We have shown mathematically the existence of this solution is an emergence of chaos. Okay, so this is one example how the spiral structure and interact with each other. Okay, so the next step we are going to think of is how the rotation affect the evolution of these ring configurations. Here is a very simple model. In order to deal with the effect of rotation, we consider the background vorticity that approximated by the m+1 zonal strip of uniform vorticity is separated by latitudinal contours, whose initial vorticity corresponds to the solid body rotation given by here. So then we tilted the ring configuration by the angle, some angle like this. Then if we are considering coupling because the background rotation and the ring configuration. So if there is no background vorticity, the ring structure can rotate around this vector. But we are going to see what happens if these strip vortices exist. This kind of model can be considered by Di Battista and Impolvani in 1998. So here is an equation. So let large x alpha from alpha 1 to m be the m contour curves representing the boundaries of the m+ zonal strips of uniform vorticity. Their initial configurations are given by here. The value of the uniform vorticity is on the each band is approximated by piecewise constant, and which is a jump across the contour curve x alpha is given by this one. This is a model vorticity distribution. And the velocity field induced by this m+1 vortex strip is represented by the boundary integral along the m contours, which is known as the contour dynamics, which is developed by David in 1988, which was very good approximation. So then we are going to consider the evolution of the point vortices, which are given in the second slide. So then we are coupled equation. This is the equation with the contours. This is the equation with the endpoint vortices. We are going to solve this equation by numerical means, and then what happens, we observe what happens. So here is a long time evolution. We consider 4 rings tilted by the angle pi over force. That means that the ring configuration is tilted by this way. Then we have a rotation direction here. The rotation direction of N ring is here, like this way. So by the coupling, as you can see, the background vorticity can be rolling up is the effect of point vortices. Okay, so we are going to show how it happens in the evolution. We are going to see the vortex path moving in a reference of frame with a solid boundary frequency. The center of vorticity vector is initially centered. Okay? This is a long-term evolution. Okay, so that means this is not a North Pole. This is the center of the rotation angle of the ring vortex. If there's no background vorticity, these 4 points rotate in the constant speed. But because of the existing rotational effect, the 4-point vortex is going this way and going backward, and then return to its position. This is the effect of the existence of background vorticity. This phenomena is can be explained by this. The retrograde motion of the low-speed waves can cause the rotational direction to briefly reverse with respect to the rotating frame. But as the vortices increase their strength by tightly wrapping the contours in the neighborhood, and the ring becomes more stronger, and then regain its rotational direction. This is what was observed in the long time evolution. In some sense, this is the effect of rotation. Okay, so it's going this way. So before moving to the second part, which I have 20 minutes, so I'm going to give some more topics on the vortex dynamics. So there is a paper on the Stewart vortex whose vorticity distribution is given by here. This is a model of sphere layers, and the analytic solution is obtained. But here is one example of the vortex structures satisfying this Stewart vortex type distribution. So we also have another paper of the vortex dynamics on sphere with boundaries. This is formulated by Darren Crowdy in 2008, in which they can deal with evolution of vortex point or vortex patches in the presence of a very complex topography. This kind of paper can be applicable to many ocean problems in future. Okay, so regarding numerical issues, we can develop some sort of the potential flow theory on the complex boundary by using a conformal map technique. So this is an example how we construct the potential flows in the neighborhood of the East Sea of Japan, okay? East Sea of China, like this. And also in the computational issues, in order to create a new an approximation method using the vortex dynamics, we are going to deal with some sort of numerical issues. I mean, we are going to, by approximating the vorticity field with many point vortices, then we need to compute the interaction of any point vortices to compute the velocity field. But this gives rise to the very large number of computational cost, which is n squared. This is a numerical obstacle to realize the point vortex approximation for on the sphere. But I have developed a fast tree-code algorithm which can be computed these point vortex interactions with n log n computed complexity. So using this kind of numerical simulation, we can realize the potential vortex flow system based on the fact that this potential vorticity is conserved on the rotating sphere. This is just topics I'm going to provide you and give you in this direction. Okay, so I have. Okay, I'm going to have several minutes. Okay, so the first stuff is something old because I have been studying this kind of study until 2012. And after that, I have been studying some sort of data analysis stuff. Now we call the topological flow data analysis. And I'm going to introduce what this kind of data analysis with a simple application to geophysical flows. Okay, the idea is here. So TFDA and topological flow data analysis is in this technology, we assign some discrete combinatorial tree structures to streamline topologies generated by the 2D instantaneous vector fields on the sphere. The combinatorial tree structure is we call COT representation. This is abbreviation of this kind of stuff. This is not familiar with many mathematical people. This is a kind of discrete mathematics. Anyway, this is a basic idea. For given streamlines like this, we can assign this kind of long sequence of letters without ambiguity, which is one-to-one correspondence. Once we have converted this data into this sequence of letters, we can recover the topological structure of this field from this COT representation. So this is a huge amount of reduction of data size, and we can use this, and each characters represent a certain vortex structures. That means we can use this sequence letters as a common language describing the topological vortex, topological streamline structures. And by using these sequence letters, we can conduct the data mining from massive flow evolution data that can be available for the identifiers in the machine learning on AI in terms of topological information. So we also quantify latent knowledge behind flow data through combinatorial structure without introducing a specific physical model. And also, by using this code representation, we have a mathematical theory predicting a future transition of topological flow patterns with a mathematical rigor. So this is a TFDA. So we are going to explain in the next few slides. Okay, so the object we are going to classify is here. This is a 2D Hamiltonian, incompressible vector fields on the spherical surface or unbounded plane. So when we introduce the stream function psi, the velocity field in two-dimensional space is given by this formula. So the gradient of psi dot u is 0. That means streamlines is a level curve of the Hamiltonian. That is a path of the fluid particle vectored by u and v. So the topological classification of this vector field is equivalent to say that we are classified streamline topologies under the restriction of Poincaré-Hopf theorem. So let us remind you what Poincaré-Hopf theorem is. This is a restriction of the indices of a vector field, which is given by here. The summation of index of a vector field at the point, singular point, xi, is always equivalent to 2 minus v. V is the number of boundaries on the surface. So these kind of conditions should always satisfied for any kind of 2D vector field on a sphere. The index of the singular point is given by this. A center point has an index 1, and saddle point has an index -1, and a saddle at the boundary has an index -1/2, and a dipole singularity 2. So by adding all these indices for all singular points on the vector field, that should be equivalent to 2 minus v. So we are going to classify all kinds of 2D vector fields under the restriction on this Poincaré-Hopf theorem. Okay, this is what we are going to do. So in order to obtain some sort of the combinatorial structure, we pay attention to a specific class of 2D Hamiltonian vector field, which is structure stable vector field. By structural stability, we mean that topological streamline patterns are unchanged under any small perturbations of vector fields, which are usually observed in many laboratory experiments and numerical computation due to noises and errors. So here is a schematic picture how we explain the difference between the structurally unstable state and structurally stable state. The pattern in the middle is structurally unstable because under small perturbations, this special connection cannot maintain. It becomes either and changes its structures and streamline patterns to this pattern or that pattern. But these patterns are structure stable because when we add some small perturbation to this structure, this connecting information has not been changed. So then by using this notion of structure stability, we consider structurally stable Hamiltonian vector field. This looks like a very specific Hamiltonian vector field, but it's mathematically shown that this class of Hamiltonian vector field is a generic class, which is dense subset in the set of Hamiltonian vector fields. So that means the classification of this Hamiltonian vector fields gives rise to a very generic classification for all kinds of Hamiltonian vector fields. Okay, so by using this structure stable Hamiltonian vector fields, we have a topological structure theorem, which stated like this. Streamlines of any structurally stable Hamiltonian vector fields in the presence of uniform flow consists of the following 4 local orbit structures. One is homoclinic saddle connections, which are given by this pattern. The second is a boundary saddle connection. This is given by this saddle at the boundary here. The third is a SS boundary saddle connection. This is an orbit from the uniform orbit flow coming from infinity to attach to the boundary, then detach to the boundary and going to the infinity. This is SS boundary saddle connection. The last one is a homoclinic saddle connection. The one orbit is coming from the uniform flow, then we have homoclinic connection like this, then going away. So these two streamline are the structure embedded in the uniform flow. This is a both, and this is a confined and bound structure attached to the boundary and figure 8 pattern. Based on this topological structure theorem, we can any kinds of structure stable Hamiltonian vector field is obtained by combination of these flow patterns. So based on this idea, we are going to give some tree structure called COT representation. The idea is very simple. In order to generate any kinds of structures Hamiltonian vector fields based on this structure theorem, starting from this fundamental uniform flow, we embed any number of these class A orbit. This is the third and fourth orbit here and there. Then every time we embed this structure into this one, we have an edges. We have introduce some tree structures from the parent node here and the child node is here. Every time we embed this structure, then we have directed edges to this structure to that structure. So as you can find, in each class A orbit, there are some other regions where we can embed any special structure like this. So then we introduce another structure called class B and class C. For class A structure, we can embed either of these patterns inside of this domain. And with this structure, we can attach this class C structure or any location of the boundaries. So by more class B and class C can be embedded in this structure, then we repeat this embedding process repeatedly until we reach to the end of the singular point. So by using this kind of idea, we are going to give the tree structure, which is called representation. Here I am going to explain how we assign. Here is an example. For a given streamline like this, it is topologically equivalent to these patterns. The big main island is given A, and B and C and D is given small circles, which is topologically equivalent. So these three islands have no structure. We have just A2 structure here. So then we can embed A2, 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 like this way. Then we also can embed the A2 structure here. And this A2 has a more internal structure, attaching the two C structure, C, 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 C. And also, this C structure can contain the B plus structure, like here. Then we have this structure contains B plus, and this small B plus contains additional B plus structure, then lead to the final dot point. So then, by using this, for this streamline patterns, we have the embedding the COT represented by this. So mathematically speaking, this kind of conversion is one-to-one correspondence. This is a uniqueness result for converting the streamline pattern into the sequence of letters. Okay, so it looks very complicated. And it is very hard to understand how do we convert the streamline pattern into word. But we have now developed a software converting the given streamline patterns to COT representation using a persistent homology and wave graph theory. So here is an example. This pattern is represented by this COT representation. This is the output of the software. For a given streamline data, so we obtain this kind of pattern, COT representation, and we also have this one. So the application point of view, this is very easy to implement. We just need the value of Hamiltonian value on discrete meshes. By using this data into the software, the COT representation is obtained automatically. So and also, this software can identify the region of influence where topological structure changes. For instance, when we say the region of influence for the pattern A plus A minus, this blue region is a region of influence. As you can see here, this blue region is region of influence with respect to this A plus pattern. Okay? So in this way, each pattern have this sort of the colored region of influence, so we can discuss how the topological structure can change using this region of influence quantitatively. Okay, so by using this software, we are going to apply this methodology to the geophysical problem. So this is the data for the geopotential height at 500 hectopascal. These are the data taken from the Japan Meteorological Agency. So this is the westerly, and this is the view from the North Pole. So we can see, and there are 5 hectopascal geopotential height given like this way. This is the height of atmosphere where the pressure becomes 5 hectopascal. So under the K-size geostrophic assumption, the radial curve of this geopotential height are equivalent to some sort of streamlines. So we can see the existence of westerly jet flow, like here, around the North Pole. And so there we can see the high and low pressure regions play a low and significant role in identifying a weather and climate system. So we can use this data to identify the state of atmospheric flows. Okay, here is our target of what we are going to deal with. This is a blocking phenomena. Blocking phenomena by Wikipedia it said here it is it is a large-scale patterns in the atmospheric pressure field that are nearly stationary, effectively blocking state, or directing migratory cyclones. These blocks can remain in place for several days, typically 4 days or even weeks, causing the areas affected by them to have the same kind of weather for an extended period of time. So in order to say the state is now, whether we can say the state now is in a state of blocks or not, it is very difficult to identify whether or not the current weather situation is in the state of blocks. Usually, they are identified by experts in meteorological authority by just looking at the 5 hectopascal geopotential height. So we are going to, sorry? Sorry?
They look at several of them.
Yeah, several of them, of course. For several days. Yes, yes. Just not one snapshot, just taking several snapshots, yeah. So we are going to apply this methodology to identify to the blocking state by using a TFDA, and then introduce some objective method to identify blocking state. Here is a target problem we are going to deal with now. Okay, so this is an example of the output of the software for a one snapshot at time T160, which is 1916 something. The date is July or something. So here is a geopotential height. So this is output of the COT representations. As you can see, the blue region are enclosed by a class A orbit, A minus and this A minus. On the other hand, this red region is also partitioned by class A orbit, which is given by A minus, A minus, A minus, A plus. And in order to identify the blocking state, we can omit the small structure. So we are going to pay attention to these big A minus, A minus, A minus, A minus, A plus structure to identify the blocking state.
How do you define small?
Okay, small structure is given by in the in the inner structure. I mean, okay.
It's inside the closed.
Yeah, inside the closed curve, yes. Then here is we are going to use some data analysis, which is a statistical way. So we are going, as I have explained earlier, the software can detect the influence and the region of influence for each A plus and A minus. So then we can extract the region of influence for each A plus A minus structure. Then we count the pixels in the region of influence corresponding to high pressure regions every 16 frames. These 16 frames correspond to 4 days patterns. So if, again, non-blocking state is described by high pressure region moves westward, yielding a thin blue spreading very thin histogram like this. This histogram means in the period of 16 frames, the area, domain of influence, region of influence moves this way. As a result of this, the histogram is very low. 4 days is coming from the expert's suggestion. We can use in a week or 2 days or 3 days and any time. But typically, blocking state is judged by...
4 days can be detected by naked eye. I would assume. If it's not everything that says for 16...
yeah, sure, okay, so yeah, we can change the dates, of course. So this is an example where we are going to compare. The idea is comparable to the expert judge. Okay? So for non-blocking state is given by this thin blue region. And this is that means this is a very wide-spreading sea region observed. So the blocking state, on the other hand, is given by this, is a high-pressure region stayed in the same area during a localized histogram. By introducing some quantity and expressing how localized this histogram, we can say this is a state of blocking or a non-blocking state. So for this time period, our approach is judged, this time period is judging as a blocking state. This is a good agreement with expert judgment, and also this is some sort of object morphological identification with COT. And on the other hand, it is very important to say this pattern is expressed by some letters, A minus, A minus, A minus, A plus. By looking at this sequence of letters, we can say this is omega-shaped blocking. So this is a side effect, a good point when we describe the pattern in terms of letters. So not only we can identify the blocking state as an expert judgment, we can say how this blocking state in the shape of omega state, or we have several kinds of blocking states. So this can be morphologically identified by just looking at the sequence of letters. This is an effect of the topological flow data analysis. Okay, we are now making this kind of analysis for the last 30 years. Then we can check if this idea can be comparable to the expert judgment now. Okay, so let me finalize my talk. So this kind of idea, and the TFDA is just now progress. It is just an ongoing project. We are now trying to apply this idea to many problems. So this gives us a complete identification of streamline patterns generated by 2D incompressible vector fields. And the computer software is developed on Python platform. That means we can apply the idea into a large amount of data by using the Python. And so we are going to now extending this idea into 2D compressible flows, and we are going to have a challenge for 3D flows, which is very, very difficult. And also we have an extended application from the industrial problems, car industry and railway companies, etc., to medical problems like medical flow data and material sciences. So we also use this TFDA analysis to conduct data-driven modeling with TFDA with machine learning and AI in future. Okay, that's the end of my talk. Thank you for attention.
Thank you very much. Questions, remarks?
I have one question, one remark actually. Can't you hear me? Oh, we are recording. Oh, I'm being recorded. Okay, I'll behave. I'll behave. Yes. No, thank you. So my question is with regard to the meteorological application, not what you mentioned here. So I would tend to think that if you show something that works automatically in identifying blocking, yes, it might be very helpful for a meteorological service of anywhere. But I think 4 days is a snitch. Everyone can do it if it's stagnant. Perhaps if you can identify it much earlier, like in 2 days, or maybe maybe 6, 4 hours, so it's a day and a half, that'll be beneficial to a Met office that can then come and say, aha, even though we can't be sure with this technique, we're able, there's a high probability that it's a blocking event, in which case, I don't know, we should issue a flooding warning or something like that. So can you say something about
Yes, thank you for that. Yeah, this is what I'm saying here. We are going to use 2 days of a shorter term and data analysis, then make some sort of the time series of the data. Then we are going to create some data-driven modeling. Then we are going to predict how this pattern going to stay in state or going away from the state. This is what I'm thinking.
questions? Thank you. I just had a couple of quick questions about your Hamiltonian structural stability results. First, I missed your definition of a uniform flow, which is an assumption in this theorem. So what was that when you say that in a in a uniform flow, these are the structurally stable patterns?
Oh, sorry.
What's a uniform flow?
I mean, a topological thing.
Sorry?
You were talking about the topological.
Yes.
Okay, sorry.
It's a bit later, yeah.
Sorry. Uniform flow is, in terms of the, I mean, uniform flow is literally the uniform flow in the two-dimensional space.
Literally.
And when we consider unbounded plane. Okay? So when we consider that the spherical case, it is regarded as a dipole singularity at infinity.
So, sorry, I missed that.
Yeah, okay.
So the definition of uniform for all these flows, because you're considering uniform Hamiltonian flows. What's a uniform Hamiltonian flow on the plane? Or?
In the plane is okay. Well, let me say that when we consider the planar case, uniform form is something like one. I mean, when we describe this in a potential flow, 1 over z is z is a stream function. Z is a
so your statement is only about flows like that, that kind of stream function?
When I say the uniform flow in the planar case, this is represented by
at infinity or something, right?
At
globally, right?
Globally,
Okay, so it's a condition,
infinity, which is the pole.
Yeah, so it's a condition on the behavior of the flow at infinity.
Yes.
Okay. The second question is that I didn't see a discussion of the boundary condition, which is important, I think, in this context, because just because you have two crossing streamlines, it doesn't mean that it's a structurally stable saddle. That can be a non-hyperbolic saddle.
Yeah. In this theory, we assume that the boundary condition is a slip boundary condition.
Okay. You assume that it's a slip boundary condition, but incidentally, locally, it can be no slip. That's still part of the slip. And when you have a no slip, say locally zero skin friction, that would give you a non-hyperbolic saddle. And if your class of Hamiltonian systems is slip boundary conditions, then there are perturbations that would eradicate that saddle. So it will not be structurally stable.
Yes, it is not structurally stable.
So then you have to fine-tune the statement a bit, because just because you have a saddle on the boundary, in this broad class of flows, which is, again, you're saying is just no penetration, right? So it's not no slip, but it's no penetration. In that class of flows, just because you have a saddle-looking point on the boundary, it doesn't mean that it's structurally stable.
See.
Right?
Yep.
Maybe that's not your statement, maybe it's that, but that's
that's
a fact.
Yeah.
You can, if you prescribe that you have no slip boundary conditions, then even a non-hyperbolic saddle, subject to further higher non-degeneracy conditions, can be structurally stable. But in the if you just say no penetration, which I think is the case, so you can have slip, then just drawing a saddle like that, it doesn't guarantee that it's structurally stable. It can be wiped out. It may not even, it's not just the topological structure changes locally dramatically. It may not even survive at all under small perturbations. So that seems to be an issue that we can discuss.
Yes, I guess we may consider the many kinds of degenerate cases on the boundary, even if we assume the slip boundary condition. But we assume the non-existence of this kind of degenerate saddle point.
Okay, thank you. Any other questions?